Paul Tatarski from University of California at Santa Cruz. And he's going to be talking about how you sift through all the information on flows coming into your network to find things that might be interesting and perhaps dangerous using an intrusion detection system.
Good morning. Everybody feeling more awake now? Coffee? The title of this talk is Needle in a Haystack. I ended up, after losing a large chunk of money yesterday at the Bellagio, I went to their art museum where I actually did see there's an actual Monet Haystacks painting in there. It gave me some solace, because I had to go back to the ATM to get into that area. So, in honor of that, it's called Needle in a Haystack. The main gist of the talk is that I'm working on looking at intrusion detection from a slightly reverse point of view. I'm looking at primarily removing potential sources of benign traffic from the flows that come into your network. My name is Paul Tatarski. There's my email address. I've been an network intrusion detection operator pretty much since 1990. My first IDS was a Sun IPC and a 10 meg tap into our backbone. I've seen a lot of packets go by, and they've got the traditional good, bad, and ugly analogy of the packets. Some of the packets that go by my network are extremely nasty, and the analogy that I'll try not to abuse too much in this talk is that the unpublished exploit stream that comes crashing into your name server and gets a shell on your main DNS server is the needle. You change root it, of course, though, so you don't really care, right? And benign or understood traffic is the hay. My belief, based on what I've been working on, is that it's easier to find those needles with less hay, but that the process of defining hay is sometimes neither easy, and in particular, it's not very safe. Just so you know the environment, I'm a pretty small shop. I'm the sole IDS operator for the University of California, Santa Cruz School of Engineering. We are growing to 2 buildings. Oh my goodness. We now have, however, several gigabit quality uplinks. We have no firewall in place, which makes us get to see all sorts of interesting things. For about the past 6 years, we've been a snort shop, so if you're familiar with snort, I will probably speak in snortese and try to define things in that IDS language. We use spans to capture our traffic. And pretty much IDS and pretty good system administration is the main source of protection for our department. So here's the problem, and actually I'll do it in reverse order. We have budgetary issues. I get money to upgrade our IDS system about every 5 years. I've got about 1.5 years to go. I need a way to better focus on unknown traffic while removing several sources of good traffic that is coming out of my department. In particular, I'm a Human Genome Project site in my organization, which is the #1 producer of outbound traffic on the campus. And we are #2 in that we have a Red Hat ISO mirror, fortunately located onto my wire as well. Our snort box is starting to run out of gas, and we need a way to find some method to extend its life a little bit farther. And we're also, due to all the worms and all the other bot fun we're dealing with on our campus, we need to start spanning internal switches. So why does that matter to a large organization? We're hoping that if we can come up with sort of a systematic way to define hay, that perhaps there's a way for large networks to apply it to their IDS system capture points if they have them, and spend more processing time and more searching time to spot the truly nasty 3 or 4 packets that are really important in that flows. So in order to start this whole process, we basically had to figure out what are we looking at for the last 15 years. And we've been trying for a long time to keep pretty good track of the top sources of flows on our network. And as we do that each year, we also sort of compare it to the number of alerts and signature matches that come off those flows, so that we can even get a feeling for, is all that traffic we're looking through every day even triggering some of the IDS signatures. If you've ever worked with snort, snort is basically a definition of maybe 3,000 needles. Base rule sets as they come. is a very specific set of packets to look for. Is what we're digging through every day even triggering that type of information? So how do you start to define hey? We took a pretty simple approach to it. We looked for systems that we manage. So I'm also a system administrator. For the flows coming out of the systems we manage, can we come up with a definition of what this stuff is? And here's a sort of example of what we came up with. We have a set of public MySQL servers, which if you've been following things lately was kind of exciting the last week. We have a large amount of regular traditional download sources. We have FTP, HTTP, rsync download sources. We do have a Red Hat ISO mirror. We have both research peer-to-peer and other kind of peer-to-peer usage. We have internet scalable file systems and some non-internet scalable file systems running a pretty good chunk of data around. We in particular have AFS. We have backups all throughout the campus, and of course we have an attempt to get everyone to automatically update quite frequently. And some other hey examples. So we have a lot of students that go make VPN connections various places, and an emerging amount of extra video conferencing and phone calls over the internet. So we also tend to do everything in our department with stuff that we can find in open source land, which has been wonderful. We purchased a fairly large, cheap IDE RAID that holds enough packets for us to do some kind of analysis on them. And we use a variety of tools after capturing them with good old TCP dump. We use, there is a slide of URLs at the end if you want to skip to that. We use TCP flow, which actually works quite well to just do a quick source dest breakout of files so you can see what you're dealing with. Snort also has a sort of not too well documented feature where you can actually put it in a session log mode, and it builds out this nice tree on the Unix file system of the data and where it went, and you can actually then use Unix like du commands to sort of get a quick view of who's sending what where. We took an old tool called TCP dstat, which gives you sort of a statistical analysis of the flow sizes and the standard deviation of the flow sizes. We use ntop periodically. We get net flow statistics from our fine central administrators on campus. And if you look at these flows long enough, you will notice large numbers of repeated large things. That's readable. For a very small sample period, we just did a quick comparison of, for flows greater than 50 megabytes in size, what was going around on our network. This is not a large network, I repeat. We had a very small number of flows that exceeded a gigabyte inside. We had a pretty good chunk of around 500 megabytes, mostly clustering up at the size of an ISO image. Keep boiling up around 50 megabyte, only 350. So all told on this slide, there's about 600 flows. During that same sample period, there were over 300,000 smaller flows, which I didn't put on the graph because I make a big funny line. And of almost all the alerts that triggered during that flow period, almost all the alerts, whether they're false positive or not, were in those 300,000 smaller flows. However, if you add up the bytes that were in those top 600 flows, we're talking 33% of all the work the capture card was doing was dealing with those larger flows. And the top 20 flows represented 7% of all our traffic for that period. So some of the traditional quick ways that we've used to define hey, if you've ever worked with LIDE-PCAP, you know you can define nice, very complicated not expressions that if you use with a tool built on top of LIDE-PCAP can, in software, prevent those packets being seen by the engine. But it assumes you know quite a bit about what's flowing where and how to define it, and if you get it incorrect, your IDS engine can completely lose those packets. Snort has a wonderful feature called a pass rule, where you can start to define very specific content level rules that say, I really don't want to do any further processing on a flow that contains Ricky Martin's World MP3 album or whatever. I don't need to look at this. Newer Snort has the ability to mark flows with what's called a flow bit, which I view as kind of a little check mark, where you can go in and say, well, I think this flow is this, and then maybe another rule says, oh yeah, it's definitely that. and you can start whittling down rows or rules that Snort uses to process those packets. But the bottom line is Snort is still reading all that information into its engine. Here's a sample pass rule just so you can see it. It just as an example, I wouldn't recommend running this. But it's a chunk of content that's in every ISO header on a CD. I've left out roughly 32,000 zeros there in front of it. But every ISO image does contain this chunk of information, and actually it's kind of interesting to put it in alert mode, and you can see how many ISOs you're coming across your network. Can I certify that someone isn't going to put 32,000 zeros in their next piece of shellcode? No, but you might see it better. Some very simple tests to show what happens just when you move around one ISO, okay? So this is a Fedora Disk 1, Disk 3, Fedora 3 Disk 1 ISO between two hosts on port 9999 with Snort in assembly mode for that port. It's a 638 megabyte flow, and I'm going to, on this graph, show you a couple of the ways it impacts. This is mostly intended just to show relative impact. Don't worry about my poor slow machine. The first line is basically a regular TCP dump. You basically see the system's working, working fairly hard. TCP dump, if I take out just port 9999, it cuts a half a point off one of the CPU system layers. No change if I take the source host address and the source port off. To show relative impact on Snort, the Snort alert rule no content check is just a Snort rule that doesn't even dig into the packet. So that's sort of a baseline that comes in around 5 seconds of user CPU time. And then as we go down the line, the next one is a Snort rule with a content field to be searched for in the packet that exists nowhere in the ISO. That word is hoptoad. There's no word hoptoad anywhere in the Fedora 3 ISO. You see that it basically matches the amount of CPU time that if you actually match a word on the ISO is the next line. And pass rules produce the same level of impact. And the last line is actually if I have 2 rules, just to show it's starting to work harder to get more done. So what we were trying to basically deal with is, sure would be nice to get this off the operating system of the machine. Can I get it out of the basically OS stack and get it perhaps offloaded someplace else? But we had a lot of concerns as we started looking for solutions for this. We really think streams are vital to doing good IDS. We really want to know, is this a orderly session of packets? Is, who's sending it? How's it going? We want to be able to stop looking at some streams after we have a reasonable degree of certainty that it is truly a good stream, or hey. And then we're big chickens. We don't trust our ability to always do this correctly. We want to cheaply and easily actually record it all anyway, just to double check periodically if we did it correctly. And our goal at the very least was to take some of our live PCAP not clauses and push them out into hardware. Started looking around, and actually I was introduced to a card from a firm called Meta Networks. It's called the MTP card. And the piece that was introduced to me is it uses Snort rules to define in its brain what it wants to capture versus not capture. And it keeps a state table of source and destination, host, and port flows, so there's some ability to know, is it part of an existing stream or not? And then as a nice cost saver for our small department, it has a backup tap on the side of it that actually acts as sort of a mini regeneration tap. You get all the packets without the filtering out that tap. And if it matches its rule sets, it hands it up to the operating system as if it was a regular Ethernet interface. Here's a glorious picture of our setup. We have the dark cloud of the outside world, my lovely Visio copy and paste switch with a span port that's pulling into the primary capture interface of the card. And then out the mirrored capture interface, I go to a pretty basic box with a large ID RAID to try to keep some degree of retrospective of the packets. We started with basically simple translation of some of the live PCAP rules that we've kept around in a file that we use for years. Most of them are actually pretty poor. But we started removing things like the backup server. Get the backup server out of there. Get all the update RPMs from Red Hat out of there, because a lot of them trigger false positives on some snort alerts. And you compile up the rules, and you load it into this card's engine, and it actually did some interesting results. The scale of this graph is a little changed. It's 3 on the far side, if you can't read there. But at the top of the graph here, we have the TCP dump of the same 638 megabyte ISO image, just as the reference point. Then we have another reference point of if I remove port 9999 from the capture. And then an interesting thing happens when I tell the card to do that for me. The CPU usage on the host drops to basically next to nothing. Well, fairly obviously, because no packets come off the card. If I then put in the same reference point of TCP dumping using the server sending back the data to the client as a reference, and then I tell the card to drop the server-side conversation, I get a pretty significant cut in CPU use. And I get enough of the information to know that there was still a large flow, but I don't have that large flow taking up my snort engine's CPU time. We are trying now to push farther into layer 3, going into the content of the packet. We'd like to take our collection of pass rules, some of which are years old, things we'd like to ignore, and we'd like to push them down into the card. And I've got kind of an example here that I may try to show with Ethereal. We would like to be able to push down into hardware a lot of the things that we were doing manually with PCAPs. We'd like to say, once we see it's one of the reasonable signatures for a large Red Hat ISO, don't bother, we don't need the data. We'd like to write dynamic rules that detect passive FTP, because we still have a large amount of passive FTP downloads, that perhaps parse the lines in the pass V section and say, there's a big data flow coming, we might not want to see it. We're trying to remove, in an intelligent way, some of the components of Windows Update, all the various Linux update services, etc. All in a goal of doing more with the small chunk of resources we have for our IDS box. I'll show you an example after I just do a couple quick summary here. The goal is if it works for us on a small scale, that it might scale up, that you might be able to produce for not as much hardware ability, the ability to capture really heavy flows and do some reasonable IDS against it. We're also hoping that if we can get very specific content rules out into the flow removal list, that you could really focus into very particular attacks against something very important in your core routers, core DNS servers. And we're also hoping that we can basically scrimp a little bit on the PC costs for the IDS system if we can offload it onto the cards. Now, I'm going to attempt to see if you can see this here. Here's the ethereal dump follow TCP stream of the Fedora 3 ISO coming across the net. Zeros! Whee! Look at all those zeros. Oh, I wonder what's going on here. And then we get this lovely message embedded in the top of the ISO, which has, as you call in the IDS business, a piece of flair, where we've got a date stamp, we've got some information, we've got a funny little MD5, and we've got this lovely warning telling me this is not the same as running MD5 in this ISO. We took basically this section of content and we made it a snort pass rule. We said, if you see this, we don't want to see any more of this flow. And compiled it into the card, activated that firmware on the card, and ran the same capture again. And what we get, it's kind of funny looking from a flow point of view, but the flow looks normal. Look at all those zeros. Whee! And then we hit the start of the marker, and chunk, it's gone. And you continue to see the conversation, and you don't see it in follow TCP stream because there's no data in it, from the client and the server, but all that rest of the roughly 636 megabytes of data is no longer in the flow. So our goal in the end is if we can come up with a rational set of rules that try to reduce some of that level of traffic, then we will be able to do much more capturing and get much more out of it. And that's about all I got. Any questions?
Hi, Paul.
Yeah.
Narendra. In my brief dealing with University of Wisconsin-Madison, they have, I think you probably know where I'm going.
I think so.
Okay, they've written some vicious, malicious traffic composition environment script, which is specifically did some comparison between Snort and Bro.
Okay.
And they found out from the reassembly of the packets, which you mentioned, from your CPU utilization, they saw Snort just took a nosedive, whereas Bro stood up to the test. But with MTP, do you see any difference there, offloading that process to MTP to the MTP card?
To be honest with you, I haven't used Bro in a while, but I've always liked Bro as a way of doing IDS. It's live PCAP based. In theory, the same removal should fly for Bro in the same way. Snort has become our IDS primarily because of its language. You see a lot of Snort rules published. A lot of our folks know how to do it.
Right.
I would be interested to find out. I honestly do not know, though, because I've not tried Bro with this card.
Okay.
Sorry to not give you
No,
yes,
that's okay.
but I think you're on the right track to try it. I would see what happens.
Okay. Thanks.
Hi, Rob Seastrom. How much do these cards cost?
This card was donated to me. I actually do not know the precise cost of this card. There is probably in the audience somewhere a gentleman who would know.
Can I get one donated to me, too?
I will again defer that to the firm that donates the card. Touche.
I'll throw in a question here. Does your IDS system, phrase it, how much does your IDS system actually catch in terms of real intrusion detections, and how do you deal with them?
In terms of what success do I get from all these piles of packets?
Mm-hmm.
My personal opinion, and folks in my department who might be here could disagree with me, is that IDS has saved a large number of our systems from compromise, and in particular has been very useful lately with finding botnets. We've put in a set of rules that primarily look for interesting patterns in IRC outbound sessions, and we have a pretty good percentage of hits on it from those one or two alerts that trigger for botnet stuff. We've done middle to not as good weeding out a lot of very specific attacks that are not automated, where people do very undocumented things that there's no snort rule for. We do, however, have a set of custom rules that focus more on what the servers say back to the attacker, and actually one of our most popular historical rules is a UID equals 0 match. It's been around forever because everyone seems to type ID when they compromise a Unix system. So I'd say overall, if we don't catch it right away with the IDS, the post-processing retrospective, we do realize at least what they did. So pretty good.
Thank you, Paul. Okay, may I have our next speakers in the panel up here, please?